Assalamualaikum dear students. This is the third lecture of Quantum Mechanics 1. In this lecture we define the short terms which we use in quantum mechanics, and these terms are most important in quantum mechanics. And the first we define what is quantum mechanics, and after that what is the wave function in quantum mechanics and probability density, superposition principle, and in the last dynamical variables. All these terms we used in quantum mechanics for further topics and phenomena and equation we find and calculate. So that's why we need to know about all these terms. What is wave function, probability density, and superposition principle, because we use all these terms in the next lectures. Students, here is the outline of our lecture, the flow of our lecture. Firstly, we define what is quantum mechanics. In the previous lecture we can define completely, explain what is quantum mechanics. Now in this lecture we only define quantum mechanics. And what is the wave function? Wave function is the mathematical tool which is most important in quantum mechanics. And the third term is probability density, which is related to the wave function. And the third term is we discuss about superposition principle, and we take overview of the superposition principle we explained in the previous classes. Now, what is the difference between the superposition principle in optics and classically and in quantum mechanics? And the last term is dynamical variables. What is the dynamical variables and how to represent the variables in quantum mechanics, and also take overview of the dynamical variables in classical mechanics, and make a difference between the representation of variables in quantum mechanics and classical mechanics in the last reference books of quantum mechanics. Now students, in this lecture we define quantum mechanics. Now I am going to give a very brief introduction of quantum mechanics, because in the previous lecture we discussed in details. Quantum mechanics is the study of microscopic phenomena such as electromagnetic waves, and in the study of subatomic particles like electrons, protons, and neutrons. Now, the main idea that we get from quantum mechanics is the subatomic particles called electrons, protons, and neutrons. What is subatomic particles? Students, subatomic particles is actually a smaller than atom is called subatomic particles, and gain or lose energy in discrete amount called photons. Now in the previous lecture we discussed about the discrete energy. What is the concept of discrete energy? Discrete energy is like steps of the stairs, like we move from one step to another step, no in between, like 1.5, 0.5, 2.5. Now we move from one stair to second stair. That's like discrete energy levels. The energy gain or lose electrons, protons, and neutrons from level 1 to another level. This is called the discrete energy levels. Now we define quantum mechanics. Quantum mechanics is a theory that determines the dynamics of material at microscopic scale. Quantum mechanics is basically a small level study of the things, because in the previous semester we discussed about the classical mechanics, the study of the dynamics of materials at macroscopic levels. No, in quantum mechanics, we study the motion of the material of the objects at microscopic level. No, the first term we define in the quantum mechanics is the state of the system. In real life, different state exist. No, in quantum mechanics, the state of a system can be fully described by wave function. Wave function is the new terms which we define in quantum mechanics, and it is denoted by psi. This is the symbol of wave function. What is wave function? Wave function. To describe a system in quantum mechanics. To describe a system in quantum mechanics, we use a mathematical entity which is called a complex function or called state vector. It is called wave function, which contains all information we need to know about the system and from which all needed physical quantities can be computed. For example, your ID card, identity card, which give all the information about you. If you know about any person, then you need the ID card, because in ID card you know about your her name and her father name, also address and date of birth. Similarly, in quantum mechanics, the wave function is called the identity card, which contains all the information which we need about the system or any system. Psi of a wave function, psi, only psi represents a wave function. If you write psi of RT, this is the wave function in the position space. R represents the position and T represents the time. In at any position at any time, if you represent the wave function, then you can write in this term psi of RT, which is equal to greater than, which is called state vector. If you write one bar and this symbol and also this symbol which is called state vector, and you can write a wave function in the form of state vector here. In the position you can, or in the students, here we define a wave function in two different ways. Wave function, it is a mathematical tool used in quantum mechanics to describe any physical system or any state of the physical system. In other words, a wave function is defined to be a function describing the probability of each possible observation, such as position or momentum. What is the meaning of this definition? For example, according to the quantum mechanics theory, every particle every matter has an dual nature. Every particle, like electron, has a dual nature, wave-like behave and particle-like behave. For example, electron show, this is an electron. Electron show particle behavior, also wave behavior. It means that if a particle move, for example, this is an particle or electron, move in this direction. According to quantum mechanics, it associated with the wave, matter wave. If electron moves, then electrons associated with the matter wave, like this. So what is the probability of finding the where is the electron in this wave? This is also the definition of wave function. So if we find some important information according to this theory and about the particle, we know about the information of this particle. For example, what is the position of electron and what is the momentum and probability. So that's why we use wave function, which is represented by psi, and some professors are called xi. So for example, the de Broglie shows the behavior dual nature of the matter, which have wave-like and particle nature, and if and the wavelength of this electron is, which is equal to, according to the de Broglie, which is equal to lambda is equal to h over p. H is the Planck constant and p is the momentum, and lambda represents the wavelength of the particle. So it is a function who gave the concept of the wave function. Schrödinger, the main scientist of quantum mechanics. Most important role in quantum mechanics is the Schrödinger. Schrödinger gives the idea of the wave function and also the Schrödinger wave equation. After solving the Schrödinger wave equation, we find the wave function of that particle of that system. So Schrödinger denoted the wave function by xi, and if we present the three-dimensional system, for example, we find the position and the time of the particle, then we represent the wave function in this form, psi rt. R represents the three-dimensional system or the coordinates x, y, z, and t is the time. It is a function from a space that maps the possible state of the system in complex number. No, the wave function is also in the complex number. We represent in the complex number. For example, wave function psi is equal to a minus iota b, because a minus iota b represents the complex number. Now here we use a term probability. What is the probability of finding the particle in the system? So if we find the probability actually a square of the wave function. So if we take a square of this wave function, then we can write psi square, which is equal to, now we solve a square, or iota square is also minus 1. So minus minus plus, so psi square, which is equal to a square plus b square. This is called the probability density of the particle. Now represent in the form of the wave or graph. So let's suppose a particle move in this form, which has associated with the matter wave. So here is the electron, let's suppose, and if particle in a box, that's like, if particle move in this box, then the associated wave represent in this form. So in the particle in the box, then we represent probability of finding probability density from this equation, and if move in the freely move, then we represent the psi square, psi into r of t. If the lambda is greater, then the momentum of the particle is less, according to this equation. This equation has less lambda wavelength, and this equation has, if we draw, has greater lambda. So if greater the lambda, then momentum is less. If less the momentum, then lambda is greater, according to this equation. And probability density can be shown in the graph type. For example, y-axis, and this is the x-axis. Y-axis shows the psi wave function, and x-axis show the position of the particles. Then we represent electron associated with a wave. This. No, if probability density, then you can show here. In the next slide, we define probability density. Probability density finds zero probability at the horizontal space. If the probability density is maximum, then it means that the particle exists at that point. This shows the x square, xi square. This is the probability density. Here is the probability density maximum. It means electron exists in this position. But at that point, electron, zero probability of electron. It means electron not here. So this is the concept of the wave function. Also give the example in the from the daily life. Example is the identity card, which gives the information about any person. No, in the previous slide, we represent the wave function from psi rt. No, what is the r? R is used for three-dimensional. So psi x, y, z into t. This is the wave function for the three-dimensional system, which is equal to psi rt, which is equal to psi x, y, z, t. If the state function is known, then every information about the particle can also be determined. So students, if we find the different information about the particles, so we need the state function or the wave function. If we know about the state function of the system, then we can get information about the particles. For example, momentum and energy. If we know about the momentum of the particles, then we can get the information from the state function of the system, and also energy. In the next lecture, we can determine the momentum operator and energy operator in the dynamical variables. So this is all about the wave function. Now we move to the probability density. What is the probability in quantum mechanics? Now students, probability density. What is the probability density? In the previous slide, we can define what is the probability density. Probability density actually the finding the information or finding the particle position or any other physical quantity where the particles exist in the system. This is the probability, means chances where the particles located in this system. So for okay, getting the information of the particles from the system, we can use the concept of probability density, because simply psi is the wave function. Simply psi's have no meaning. So for finding the wave function or state function of the system, we use probability density, which is equal to the square of the wave function of that system. So we define the state function, we define the wave function of for three-dimensional system is psi rt. Now, if we find the probability density, then we take square of the wave function. So it means psi has no meaning. For example, if we write psi only a meaningless quantity itself, has no physical significance or meaning. So if we write psi xyzt or simply rt, it shows three-dimensional system, wave function of the three-dimensional system, so which has itself no meaning. But if we take square of this psi, it has a meaning. In 1926, Max Born stated that at any time t, the probability of finding a particle between position in space is equal to psi rt squared d cube of r from minus infinity to plus infinity, which is the limit of the particle which exists in the system. So we can read these lines. The quantity psi rt squared d cube r. Now we use d cube r for three-dimensional system, represents probability of finding the quantum mechanical system in small volume element at center r at time t. So it small volume element which exists at center r and time t. So the quantity minus infinity to plus infinity is the limit of that wave function or probability density psi rt squared d cube r represents the probability of finding the quantum object somewhere in the whole system. If we can find this probability density, then we can say that the particle exists in this whole system here. If this probability density, which is equal to 1, what is the psi star? Psi star is the complex conjugate of that psi, the complex conjugate of the wave function. D cube r, which used for three-dimensional and for using the volume element, and we can also write d cube r which is equal to dv. So if we find this function after the numerical solution, which we get the solution which is equal to 1, it means that the wave function is called normalized. This condition is called normalization condition. What is the meaning of normalize? It is used to determine the constant which is multiplied with wave function. Now in the next lecture we define normalization conditions and what is the meaning of normalize. Here only the small concept of normalized condition. Okay, I hope so students you know about what is the probability density and what is the wave function. Now students, here is the activity for you. You have 15 minutes. So take overview of all these terms, double slit experiments, interference and the superposition principle in the book of second year and from the net. After that we discuss these terms because in quantum mechanics makes a difference between superposition principle and the superposition principle at classically point of view and in quantum mechanics. What is the difference between these? So that's why you can read from the internet or second year book these topics. Then after 15 minutes we can continue our lecture. What is the superposition principle of quantum mechanics? Now students, the next term is superposition principle. You all know about the what is superposition principle in the previous class second year physics. What is the superposition principle? In the second year class we know you all of know about the superposition of principle of two waves is when one wave move and the second other waves also move, then you combine and the resultant of the waves increase the amplitude of the wave. This is called the superposition principle. Now in optics superposition phenomena, let us we have two waves. First wave is in this pattern like this is the first wave, and second wave is also in this pattern. This is the first wave, this is the second wave. In this pattern, if you combine or add these two waves, then the resultant wave is resultant wave means increase the amplitude of the waves. This is known as the superposition principle in optics. Similarly, the same concept we used in the quantum mechanics, the superposition principle in quantum mechanics. Now, before we start the superposition principle in quantum mechanics, some question discussed here. For example, in second year class physics we explain the phenomena of double slit experiments. Here the question is that how do we count mathematically for the existence of the interference pattern? You all know about the interference pattern in the double slit experiments with material particles such as electron. For example, in the double slit experiments, electrons come and electrons, this is the electron, and you place two slits. This is S1 and the second one is S2. When electrons come, and question is electron pass from slit 1 and slit 2, but when electrons and shows the interference pattern here. Why electron shows the interference pattern here? The electrons has a field. Electrons move in the form of waves and having a field, and also pass from slit 1 and slit 2. So in quantum mechanics, the S1 is the wave function of 1 and S2 is the second wave function of the slits. So if we combine the wave function, then we present the superposition principle. So mathematically we measure the value of this quantity of this wave functions and values in the form, how to write in the form of the equation we here know about. It can be represented, for example, the state of a system does not have to be represented by a single wave function. So if we represent a state of the system, then only give wave function, we cannot represent this state of the system. So we need two wave functions and many other two or more wave functions for representation of this, and this is also called the superposition of two or more wave functions. Simple definition of the superposition principle in quantum mechanics is that the superposition principle states that a wave function psi can be expanded as a linear combination of the normalized eigenstates. What is the eigenstates? Eigenstate is a quantized dynamic system such as atom, molecule or crystal in which one of the variables defining the state such as energy or angular momentum has been determined fixed. For example, in the next slides we present mathematical form of superposition principle, and here we know about what is the eigenstates and what is the wave function and linear combination of the superposition principle. So here is the example of superposition principle from microscopic world. For example, we discuss about the classical mechanics. The example should be given from the classical mechanics. From macroscopic world is a vibrating string. Its state can be represented by a single wave or by the superposition of many waves. Vibrating string is the example of this superposition principle. For example, the vibration states of the guitar with two strings is a superposition of the two strings frequencies. This is the example related to the guitar of two wires and two strings, and vibration of these strings makes the superposition of two waves. So now students, here is the representation of superposition principle in quantum mechanics. Let us consider two wave or state function. The first one is psi1. If we have two state functions psi1 and psi2, psi1 represents the first wave function of wave 1 and psi2 is the second wave function of wave 2, representing different states of particles. For example, then linear combination is also a state function. For example, if two add two state function, then the resultant wave function state function is also a state function of linear combination. This is known as the superposition principle in quantum mechanics. Now, psi represents the state function of whole system when we add two state function. C1 psi1 plus C2 psi2. This is the linear combination of the state function, and this is the formula of representing the superposition principle in quantum mechanics. Now we use term state eigenstates. Here psi1 and psi2 is the eigenstates of this equation. Now the more concept about the eigenstates or eigenvalue in the next lectures. All principles are explained by classical as well as quantum, but superposition principle cannot be defined by classically but can in quantum mechanics. The application of the superposition principle is the particle in a box. If particle placed in a box, what is the superposition principle of these particles? Now students, if we have many students, the next term is dynamical variables. What is dynamical variables is most important in quantum mechanics. The definition of dynamical variables is the measurements of every physical measurable quantity. It means that every physical quantity which can be measured is called observable or dynamical variables. It is second name of dynamical variables is observable. it means if we observe anything and you should be measured, it means dynamical variables. Where corresponds on operator A, any operator you can write in the form of this with the alphabetics with the cap, whose eigenvector form basis. What is the eigenvector and basis? We discuss in the next lecture. No, simply we say that every dynamical variable is associated with a linear operator which can operate on wave function. It means operator can operate the wave function. Represents the dynamical variables. The only possible values for an observable are operator. In the previous slide we say that an operator operate the wave function. So here we write operator. This is the wave function which denoted by psi, which is equal to Meyer's value and multiply by psi. Operator is here Hamiltonian operator. H is represented by Hamiltonian and cap should denoted by Hamiltonian operator H into psi is the wave function, which is equal to E is the energy value, measurable value, and psi is the wave function. This is simply equation is called Schwinger wave equation for linear combination. So Meyer value is also known as eigenvalue and psi is eigenfunction. So this denoted by psi, this is the wave function which is denoted by eigenfunction, and E represents the value which should be measurable is called eigenvalue. So this is the method of representation of dynamical variables, and some other dynamical variables representation we saw. Representation of variables. Some variables which is represent in classical mechanics and in quantum mechanics, and you can make the difference between the classical representation and quantum representation. So variable is position. Every particle has a position. Let's suppose a particles move from x to delta plus x. This is the position of the particle, and of the subatomic particles like electrons, protons and neutrons. And momentum is also a variable which should be measurable quantity. So momentum is represented by P, capital P, and energy is also a value of the particles which are moving at some position and having some momentum. So these are the variables. Variables means dynamical variables which should be measurable. So classical mechanics representation is students only position represents by small x in classical mechanics, and momentum represented by P is equal to mv. M is mass of the object and mass of the particle. V is the velocity of the object and V is the velocity of the particles which is moving. And we know that about what is the velocity. Velocity is the rate of change of displacement. So we can write momentum P is equal to m dx over dt. This is the classical representation of momentum. So energy is equal to the sum of the kinetic energy and sum of the potential energy. And kinetic energy is represented by T and potential energy is represented by V. And simply students, you know that the kinetic energy which is equal to half mv square and the potential energy is equal to mgh. So this is the classical representation of the variables. So what is the quantum representation of variables? This is the most important. I can say in the first lecture The quantum representation is most important in quantum mechanics. When you write numericals and solve these numericals, the most important things you should be mind and remember that the representation of variables in quantum mechanics. You cannot write only small x for the variables. Always write cap on the x. This is the representation of quantum mechanics. So, the quantum mechanics position of the particles is represented by small x and had a cap on the top of the x. So, this is the quantum mechanics representation of the position of the objects or the particles. So, momentum representation is P and had a cap on the top of the P, which is equal to minus iota h cut into delta. Delta is only equal to, no, here I can write delta is equal to curly over curly x plus curly over curly y plus curly over curly z. For 3-dimensional. So, if we find the momentum in the position of the x-axis in the x direction horizontally, then we can write P of x, the position of the momentum in quantum mechanics representation of the position of the momentum in the horizontal direction. So, P of x, which is equal to minus iota h cut curly over curly x. If we represent the particles at the vertical position, then we can write P of y, which is equal to P of y cap, which is equal to minus iota h cut curly over curly y. Similarly, in the z direction, P of z cap, which is equal to minus iota h cut curly over curly z. So, all these combined, then you can write P, capital P on the top of cap, which is equal to minus iota h cut del. This is the quantum mechanics representation of momentum. So, the energy representation of classical representation of energy, which is equal to E is equal to T plus V, kinetic energy plus potential energy, but in the quantum mechanics, the representation of energy, which is equal to E cap, which is equal to minus iota h cut curly over curly t. Sorry, E cap, which is equal to iota h cut curly over curly t. In the momentum operator, students keep in mind, in the momentum operator in quantum mechanics, you can write minus sign, but in energy operator, you can only write plus iota h cut curly over curly t. How to find this representation of quantum mechanics of momentum and energy? So here is the derivation of the momentum representation of quantum mechanics in quantum mechanics and also energy operator in quantum mechanics. P is called in quantum mechanics momentum operator and E is also called the energy operator. So the derivation of these all operators we should be solved in the next lecture. How to find this value minus iota h cut curly over curly x of the P of x and E, which is equal to minus iota h cut curly over curly t. How to find these values? I can calculate these values in the next lecture. So all these representation of the variables in and make a difference between the classical mechanics representation and quantum mechanics representation. In quantum mechanics, operators and the representation with the cap is most important. when you write the position, momentum, energy, and any other operator or variables. Now students, these are the reference books of the quantum mechanics, Zitli and quantum mechanics concepts and applications. Most of the data I have collected from this book, Zitli, and you can also search these topics from all of these books. And I hope so today lecture you have clear all the points related to what is the definition of quantum mechanics and the wave function, which is the most important tool, mathematical tool of quantum mechanics, and the probability density. Also, what is the superposition principle of classical mechanics and the quantum mechanics, and what is the difference between the superposition principle of classical mechanics and the quantum mechanics, and also what is the representation of dynamical variables, and how to represent in classical mechanics and how to represent in quantum mechanics. In quantum mechanics, the representation of variables is most important, and the different method to represent these variables in quantum mechanics, the most important. If you write any variable in quantum mechanics, you should be cap on the variables, on the top of the variables. If you not write, you can simply say the position, for example, the position of the momentum and the position and the energy value of the particles in classical mechanics. If you write the cap on the top of the variables, then it means that you can represent in quantum mechanics. I hope so you can understand. If you have any problem in this lecture or any point, then you can ask me on comment box. So much. No students, we meet in the next lecture. Inshallah. Allah Hafiz.